Looking at aims and hypotheses. So it's going to be a little bit of a recap on what we covered at the beginning of our lower sixth year when we looked at different types of variables and writing hypotheses. And this is going to be particularly important as we move on to look at inferential statistics. So just to recap our different types of variables. So remember that our independent variable, or otherwise known as our IV, is the variable that the researcher is manipulating. So quite often we have different levels of our IV, which means the different conditions to which participants are allocated to in an experiment, either the control or the experimental. And our dependent variable, or our DV, is the variable that our researcher is measuring. So we're really, in the experiment, looking at manipulating the IV to test the effect on the DV. It's really important that we clearly operationalize our variables, and this means that we clearly define them. So in the case of the independent variable, our IV, we have to clearly define this variable in a way that will allow us to manipulate it. And for our dependent variable, we need to clearly define it in a way that will allow us to accurately measure it. So quite often in psychology, we have some very abstract concepts. For example, intelligence or happiness. So it's the job of the researcher to make sure that they clearly define exactly what they mean by intelligence and happiness, and exactly how they're going to manipulate or measure it. So for example, if we're going to measure the effect of intelligence on, for example, A-level results, we want to know exactly how intelligence is going to be manipulated in the case of the IV. So in this case, we're going to manipulate our intelligence in terms of the score on the Alfred Binet IQ test. For example, if we're measuring happiness, so in this case, happiness is going to be our DV, we need to know exactly and precisely how happiness is going to be measured. And in this case, we've defined that as our score out of 7 on the Henry Affect Scale. So this is very, very important for us as researchers, so that our findings and our studies can be replicated, so that future researchers know exactly how we manipulated our IV and exactly how we measured our DV. And for you doing your A-level, it's going to be really important for you to be in order to accurately write your hypotheses. Just a recap on aims, and then we'll be able to compare aims to hypotheses. So our research aim is a precise statement of exactly why the study is taking place. It's common practice and good practice to include both your IV and your DV in your aim, but note that in an aim, these don't have to be operationalized. It's usually very concise, it's usually just one sentence, and it's usually just the more abstract, non-operationalized concepts. So for instance, if we go back to our previous examples, we had intelligence and happiness. This is what would appear typically in the aim, rather than IQ as measured by the Alfred Binet scale and happiness as measured by the Henry Affect Scale. So some examples of aims here, they usually start with to investigate or to measure. To investigate the relationship between exercise and weight. So notice here that because we're looking at a relationship here, this is indicating that this is going to be a correlational study. And to measure the effect of CBT on the severity of depression symptoms. So they usually start with to investigate or to measure, and we've usually got non-operationalized variables there in that aim. Hypotheses are precise, testable research predictions. So an example here, a caffeine consumption will increase reaction times. So we're saying here what our variables are and what effect our IV is going to have on our DV. There are different types of hypotheses that we need to be aware of. We've got our null hypothesis and an alternative hypothesis. And we've got two different types of alternative hypotheses, directional and non-directional. All of this is particularly important when it comes to inferential testing. Let's start with our null hypothesis. So the null hypothesis is a statement to predict that there will be no difference or correlation between conditions. Let's just break that down. So if we're talking about there being no difference between conditions, we're referring to an experiment. And if we're saying that there will be no correlation, we're obviously referring to a correlational analysis. So for our correlational analysis, we're basically saying that the correlation coefficient is going to be 0 or close to 0 and non-significant. If we're saying that there's no difference in an experiment, we're saying that the findings, the results, the DV between the control and our experimental group is negligible. There's not likely to be any major difference or any significant difference between the findings there. So an example of a null hypothesis, there will be no difference in the reaction time of students who consume caffeine and those that do not. So no difference here is key. The reason that we use a null hypothesis in experimental research is because this is kind of the baseline. We generally expect that the null hypothesis will be true, and any findings that contradict that, so any findings that do suggest that there is a significant difference, for example, between the control and the experimental condition, means that we reject our null hypothesis. So in any experiment, we're always going to accept one hypothesis and reject the other. So it's important that we always include both a null hypothesis and an alternative hypothesis so that we can accept one and reject the other, depending on what our findings and our inferential statistics indicate for us to do. This is the method for writing a null hypothesis for an experiment. And notice that there are different ways that you'll need to phrase these, depending on whether it is an independent groups or matched pairs design, or whether it's a repeated measures design. It's a very, very subtle difference, but the key thing to note here is that for independent groups and matched pairs, we've got different participants in each condition. So we've got some participants in the control condition and different experiments and different participants in the experimental condition. For a repeated measures design, it's the same participants taking part in both conditions. And so our phrasing is going to reflect that. So for our independent groups and our matched pairs design, there'll be no difference in reaction time for A-level students who consume 5 milligrams of caffeine compared to those who consume 0 milligrams of caffeine. So here it's very, very clear that there will be no difference, indicating that this is a null hypothesis. We have our dependent variable, our reaction time, and exactly how that's going to be measured. We've got our population. Notice here that we don't include the number of participants. We just include the population from which our participants were drawn. Never include numbers of participants. So we've got no difference, our null hypothesis, our reaction time, our dependent variable, our population, and then we've got our levels of the IV. 5 milligrams of caffeine and 0 milligrams of caffeine. Likewise, same experiment, but this time we're using repeated measures design. There'll be no difference, a null hypothesis, in reaction time measured in seconds when A-level students consume 5 milligrams of caffeine compared to when they consume 0 milligrams of caffeine. So it's exactly the same idea, but we just need to slightly change our phrasing to reflect different participants in each condition in the independent groups and matched pairs design, and the same participants in a repeated measures design. Let's have a look now for how we would phrase a null hypothesis if it was a correlational study. So, for example, there will be no relationship between height, measured in centimetres, one of our covariables, and IQ as measured by the Reynolds Intellectual Assessment Scales in A-level psychology students. So here we've got no relationship, indicating this is a null hypothesis, and we've got clearly operationalised covariables, as well as our population. An alternative hypothesis, on the other hand, is a statement that says that there will be a difference, or there will be a correlation. So our null says that there will be no difference, or no correlation. An alternative hypothesis says that there will be a difference. And there are different types of alternative hypotheses. We could either have a non-directional hypothesis, otherwise known as a two-tailed hypothesis, or a directional hypothesis, which is a one-tailed hypothesis. The key to remembering these, a non-directional hypothesis is like a two-tailed fish. It's non-directional. Two-tailed fish, it's not going anywhere. So two-tailed fishes are non-directional. A one-tailed fish can swim in a direction. It will be able to go. So one-tailed is directional and two-tailed is non-directional. So, how do you choose your hypothesis? How do you know whether you should use a non-directional hypothesis or a directional hypothesis? There's a few rules, and this is a very, very common question and one that students quite often get wrong. We use a non-directional or a two-tailed hypothesis when we actually don't know what effect the IV will have on the DV, or whether there's likely to be a correlation. So this happens when either there's been no past research into your investigation, your aims, or the previous research has been inconclusive. Perhaps there are mixed findings and it's still not clear which direction it's going to go, what exactly the effect the IV will have on the DV. So we use a non-directional when there's either little or non-conclusive past research. We adopt a directional hypothesis or a one-tailed hypothesis when the previous research does indicate which direction it's going to go, so what effect the IV will have on the DV. So let's have a look at the different ways that you're going to be writing a directional hypothesis, otherwise known as a one-tailed hypothesis. So a directional hypothesis is a prediction statement or hypothesis that states the direction or how the difference or a correlation will be shown. So for example, caffeine will increase reaction time. So if we're writing this for an experiment, here again we've got the same experiment as before, the effect of caffeine on reaction time. So we're going to break this again into our independent groups and matched pairs compared to a repeated measures design. So directional is saying that in this case caffeine is going to affect reaction time. So let's have a look. So A-level students, our population, who consume 5 milligrams of caffeine will have a faster reaction time measured in seconds than those who consume 0 milligrams of caffeine. You can tell this is directional because we've got a term here like faster. Anytime you see something like this, a comparative term, faster, slower, more, less, quicker, slower, greater or smaller, we always know that it's going to be a directional hypothesis. In a repeated measures design, it's the same deal, but of course we've got the same participants in each condition, so we're just going to phrase it a little bit differently. Again, we've got our population, A-level students, will have a faster reaction time measured in seconds when they consume 5 milligrams of caffeine compared to when they consume 0 milligrams of caffeine. So notice that we're including the same information each time. We're including our population, we're including our operationalized IV and DV. And in the case of a directional hypothesis, we're saying a comparative term here. So we're saying exactly what direction the experiment is going to go, exactly what effect the IV is going to have on the DV. In this case, more caffeine leads to faster reaction times. And that's because we know from previous experiments and previous research that that's the likely effect we're going to observe. In the case of a correlation, we're going to be including basically the same information. So let's just have a look at this one. So there will be a positive correlation between height measured in centimetres and IQ as measured by the Reynolds Intellectual Assessment Scales in A-level students. Again, we've got our population, A-level psychology students. We've got a positive correlation, so we're saying here exactly what direction it's going to go. Of course, we could say here there'll be a negative correlation, but we've chosen, based on previous research, to assume that there will be a positive correlation. And then we've got our very clearly defined covariables, height measured in centimetres and IQ measured by the Reynolds Intellectual Assessment Scale. So there are different examples of directional hypotheses for experiments and correlations. Let's have a look now at non-directional hypotheses, or otherwise known as two-tailed tests. So a non-directional hypothesis is a prediction statement or a hypothesis that does not state the direction that the IV will have on the DV, but does say that there is going to be some effect, or there will be a correlation. So in this case, caffeine will affect reaction time. We know that caffeine is going to have some effect on reaction time. We just don't know what that effect is actually going to be. Is it going to increase reaction time, or is it going to decrease reaction time? We don't know. We're not confident enough to say exactly what direction that's going to go. And that's because there's no conclusive previous research to indicate what direction that will go. We're still going to say that it's going to have an effect, we just don't know which one. So let's have a look at how we would write that for an experiment. So for an independent groups or matched pairs design where we've got different participants in each condition, there will be a difference in reaction time, measured in seconds, for A-level students who consume 5 milligrams of caffeine compared to those who consume 0 milligrams of caffeine. Again, we're still including the information about our population, A-level students. We're including our operationalised DV, our reaction time, and we're including our operationalised IV, our 5 milligrams compared to 0 milligrams of caffeine. But rather than saying that it's going to increase reaction time or it's going to decrease reaction time, we're simply just saying that it will result in a difference in reaction time, but we don't know what that difference will be. For a repeated measures study, it's the same idea. There will be a difference in reaction time measured in seconds when A-level psychology students consume 5 milligrams of caffeine compared to when they consume 0 milligrams of caffeine. Once again, we've got our population, our operationalised IV and our DV, and we're saying that there's going to be a difference. We just don't know what that difference is. And let's have a look for correlations. So again, we don't know exactly what the correlation is going to be, whether it's going to be positive or negative, but we know there will be a correlation. So we're saying here that there will be a relationship between height measured in centimetres and IQ as measured by the Reynolds Intellectual Assessment Scales in A-level students. Our population, our operationalised covariables, and the fact that there will be a relationship. We just don't know whether that's going to be a positive or negative relationship. So, just finally some tips as you go off and practice writing your own hypotheses. Always, 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 always operationalise your variables. There's no excuses for not doing this. In the case of the DV, you're saying exactly how you're going to measure this DV, whether it's going to be in seconds, whether it's going to be in number of items correctly recalled, whether it's going to be the percentage accuracy. It doesn't matter so long as you clearly define exactly how it's going to be measured. In the case of the IV, you need to be very, very, very clear exactly how you're going to be manipulating that independent variable. And this usually involves, particularly in an experiment, outlining the conditions of that experiment. So what are the control condition going to be exposed to, and what is the experimental condition going to be exposed to? You need to very, very clearly outline exactly the difference between those conditions there in order to operationalise your IV. So that's what I mean here in this second dot point. Include the levels of the IV. These are our levels here. Sometimes, quite often, you just have two, a control and one experimental group. But in other studies, you might have a more complex design where you might have a control group and 5 experimental conditions. For example, in Loftus's study, the car crash study, where she had 5 different verbs of impact. In that case, there were 5 levels of the IV, and it would be important in your hypothesis to include all 5 levels of the IV there. We need to include the population and not the sample. So say where your participants were drawn from. For example, they were A-level psychology students, or they were males studying economics at Brighton University, but we never include the sample. We never say how many participants were taking part in the study, just the population from which they were drawn. So some examples here. So A-level psychology students, this is our population, who study for 15 hours per week, our first level of the IV, will achieve a higher grade on their mock exams, our operationalised DV, than students who study for fewer than 5 hours. So we've got all of our elements here. We've got our operationalised IV, our levels 15 hours a week compared to fewer than 5 hours per week. We've got our population, and we've got our dependent variable here as well, the grade that they achieve on their mock exams. And for those of you that have been listening attentively, you'll know as well that this is a directional hypothesis, because here we've stated the direction that this is going to go. We're saying that those who study for 15 hours per week will get a higher grade than those who only study for 5 hours a week. So we know, based on previous research, that studying more leads to high grades on mock exams, which is why we've adopted a directional hypothesis for this study. So your homework is going to be to practice writing different hypotheses, null and alternative hypotheses, directional and non-directional, because it's very, very important that you can understand the subtle differences between these in order to write successful hypotheses, but also when it comes to determining what type of inferential test you're going to be using. So it's important to get this right.